observation. We are live streaming. Okay. So this is how we can, let's say, deal with our observation. How we can digest them in a way that can be connected to the theory. But now we have to do the other part. So given that we have two observable X and Y, so for example, galaxy position, galaxy shear, we know how their correlation function is built, what I was showing you before. And we can express it, remembering that inside these fields, we have our density perturbation. You can show that you can express these CLs theoretically as a function that depends on the primordial power spectrum, so what we have at the beginning of times, if you want, and some transfer function, these W's, that contain basically how these perturbations evolve with time and the specification of how you observe these two fields. I will show you later in this talk how there are some approximations that can basically allow you to write this in a much more convenient form. And basically you can, from your theory, get your CLs, your correlation function, simply as a function of your matter power spectrum, your Hubble rate, your comoving distance, so three things that can be obtained from your theory, and as a function of two window functions here that are related to the things that you are observing. So in particular, for what we want to do, so galaxy clustering and cosmic shear, these window functions, this kernel function here, these W's, take this shape. Basically, in one, you have the galaxy window function, which takes into account with this bias, with this galaxy bias, that your galaxy field is a biased proxy of your matter field. So your galaxy power spectrum is related to the matter power spectrum this way. So these plugged into the equation before will give you galaxy clustering correlation functions that you can compare with the data. And in the same way, you can build one for the cosmic shear, which you have, in which you have a part that describes the shear on your images done by the intervening matter, and an intrinsic alignment part that basically is an astrophysical effect due to proximity of galaxies. This is mostly considered a nuisance to your expectation. It's something astrophysical that you have to subtract in order to reconstruct precisely the matter field. Basically, with all these ingredients, if we have our cosmological model, we have the specifications of our survey, we can construct this correlation function and compare them with the data. Now, if we were working with real data, this would be enough, right? You just get your observables from your survey, you create your theoretical prediction with your model, and you just compare. With forecasts, obviously, we don't have the data. We have to work around it. And this can be done either by simply simulating our data set, so creating synthetic data set through n-body simulation, or even more naively, just assuming a fiducial cosmology and creating our CLs. And then we run an MCNC like one would do with real data. Or one can use the shortcut, let's say, of the Fisher matrix. Basically, we can build, assuming our posterior distribution of the parameter to be Gaussian, we can build what is called the Fisher matrix, which is simply the second derivative of the likelihood on your parameters, so something that we can obtain theoretically, and obtain the constraints. Going a little bit more in detail for this, why do we use the Fisher matrix? The Fisher matrix has the advantage of being fast, so one can obtain constraints on forecast on constraints very fast. You don't have to run a whole MCNC. It can be written easily for the CL approach that that I've shown you. So basically, starting from this equation, so a second derivative, you end up with something that only contains first derivative of your CLs. So this is something that you compute theoretically. You can do your derivative, and you have inside a covariance matrix where the specification of your experiments get in. So for example, your modeling of the noise, the sky fraction, how many galaxies you are going to observe. You can plug in the details of your experiment, plug in your cosmological model to perform the derivative, and you end up with the Fisher matrix. The Fisher matrix is just the inverse covariance of parameters, which means that once you construct this object, you can extract all the uncertainties that you expect from your parameters from your survey. If you want more detail on this, this is basically the paper of the Euclid survey where we validated all our codes. It was a 4-year effort to validate all our codes for Fisher matrix and get the, let's say, the official forecast for Euclid. And inside, we try to have a walkthrough of how to build Fisher matrices. So if you're interested, go there and you can find all the details. So using this approach, what we get is the expectation, what we expect of constraints coming from future survey. And this is something that we did for Euclid, and we knew already, but we found out how amazing Euclid is, obviously. And one thing that is interesting to see from these results that we got is the importance of the cross-correlation between different proofs. So in the formalism I shown you before, let me go a little bit back, sorry. But in this formalism that you see here, we can obviously get the correlation function, for example, galaxy-galaxy, just the position of the galaxy. But we also can get the cross-correlation between these. So having one field that is the galaxy position and one field that is the shear of the galaxies, which means that we can cross-correlate this information and obtain additional information. What we have shown in our Euclid work is that this cross-correlation, this XC that you see here, is extremely important. Already you see that for some of the parameters, having the full set of photometric observation, this weak lensing plus galaxy lensing plus cross-correlation, it's enough and doesn't get improved when we add the spectroscopic surveys of Euclid to the mix. You can see this, for example, on the W parameter, so a parameter of dark energy, in which adding the spectroscopic galaxy lensing doesn't bring much. So it shows you that for some of the parameters, already the photometric survey alone could be enough to get extremely powerful constraints. This is an interesting result that we found, and we went a little bit forward looking at what this full correlation, the 3 times 2 point, the so-called 3 times 2 point combination of photometric observable can give us. Because if we look at its constraining power, especially when we look at the intrinsic alignment part, so the nuisance parameter, it's extremely important. And this is because we know that these astrophysical effect, intrinsic alignment, goes and impact the weak lensing, but it doesn't affect a lot of the galaxy clustering. So mixing the two information together, we can obtain tight constraints on these. And this basically means that the photometric survey of Euclid, but any photometric survey you want to work on, if used to its full power, let's say, can tell us a lot about cosmology and a lot about astrophysical effect as well. So it's extremely, extremely powerful. So any question before I move out of the optimistic part? Okay.
When you do this 3-point correlation function, usually you have to know the data, it's consistent. But since you are doing simulation, how does it work? Do you need to do that, or it's all?
So this could be an issue indeed. We have to remind that here, for the moment, in this forecast, we are assuming basically that the galaxies on which we do the position correlation function and the galaxies on which we get the shape are the same set. So basically, this creates necessarily a consistency between the two. That you are accounting for the fact that it's the same set when you do the cross correlation. Indeed, if you cross correlate different surveys, which can be done, it should be done, this is an issue that has to be taken into account. We are not doing it here because we are in the same using the same observation for the two fields, but it's something that one has to take into account.
Okay, so you don't have to be bothered by internal consistency because the way you frame the problem, it's already taken into account. Okay.
In this work, yes, this is something that whoever needs to be taken into account, at least checked when you have the real data.
Okay, I see.
Okay, so let me go forward if there are no other questions. And after a nice optimistic part telling you what photometric surveys will be great for, let me go for a bit of issues. So how could things go wrong? I mean, we have everything under control, everything, we expect fantastic constraints and so on. The problem is that given the increase in precision, sensitivity, sky coverage of our observation, we are going to face problems that we didn't have before, in the sense that accessing different scales with much smaller error in our observation will show approximation effects that were neglected, that were not important in previous surveys where the sensitivity was lower. So basically, what I'm focusing on here are basically issues related to the fact that we are accessing different scales from before, both on the small scale side and on the large scale side. So on the one hand, accessing smaller and smaller scales that we are able with an increased resolution of our experiments means that we are going deeper and deeper in what is called the nonlinear regime. This is a regime where basically the approximations we do for our theoretical approximation break down. And this comes from the fact that all our predictions at the theoretical level are done assuming that perturbations are small, so that delta, the overdensity, is much lower than 1. And this allows to make our calculation very simple, and we can go all the way in computing all our theoretical prediction. But this fails when we go to nonlinear, where this assumption that delta is much smaller than 1 breaks down. And this is an issue that we have to face. On the other hand, where we go to larger and larger scales, and this is something that the new surveys will have accessible, the approximation that we've done to compute our correlation function, our CLs, will break down, and we have to take into account additional effects. A large scale, general relativistic effects start to become relevant. So we have to take many things into account, and this can break down all our nice forecasts. Why didn't we see that before? So let me talk a little moment of the perfect world of CMB. Why do we like CMB so much? I was in Planck, so I like CMB quite a lot. And the reason for that is that CMB has several advantages over everything else. It's well understood physics because we are talking about recombination physics mostly. So in a sense, you're talking about atomic physics. The unknown component that we have in the universe, dark matter, dark energy, are there, but let's say that most of their effect happens on secondary anisotropies, so on the effect of lensing, on the amount of matter that you have in the problem. Dark energy is not that well constrained by CMB because it's only tiny effect. Also, we are at a redshift, so it means that the perturbation didn't have much time to grow from the initial seed. So we are in a small perturbation regime. Everything is linear. We can do all our calculation perfectly. And all the foregrounds effects have been thoroughly studied and we can model them. So it means that this is a very nice setting to do a cosmology, while in larger scale structure, we didn't deal with most of these things yet. So if you look at this plot, for example, and look at the matter power spectrum, so you see here in dashed, you see the nonlinear matter power spectrum. When they start to diverge from each other, it's where the nonlinear regime starts. Now, if you look at where Planck temperature constraint sits, you see they come from here up to here, more or less. Now, if you look, for example, at BOSS or SDSS constraints, where the point can be related to the scale, you see that we are all in this regime. So you notice that the problem is that CMB was fine living in an area, in a regime where everything is easily modeled, why we have some more issues. And small scales are quite an issue, because if we don't have a way to go from our cosmological model to prediction for the observables, we don't really have something to compare with data. We cannot simply use the Poisson equation that I was showing you before. And in order to obtain the matter power spectrum to compute our theoretical expectation for the observable, we need n-body simulation. So you need to perform an n-body simulation, correct your linear matter power spectrum with what the simulation tells you, create, I don't know, fitting function to construct this, and then use it to constrain it to compute your observables. And this is not the only issue, because then at small scales, also baryonic feedback become relevant. If you go at small enough scales, what you have is that supernova explosion, gas dynamics also affect how matter is distributed. So you have to take this into account as well. You need hydrodynamical simulation. So basically, it means that everything that we do is related to the kind of simulation that we do. But to do that, what we need is assume a cosmological model. So what happens if your simulation is done with a model that doesn't actually go well with the reality of your universe? What does it happen? Do we get accurate results? Not precise this time, accurate. Do we get the good results? So what we have shown in this work, I don't know if you can see because I have a bar here, but yeah. Oops. What we've shown in this work, what we have tested is we constructed data for Euclid with lensing, creating the nonlinear regime data with one of the tools that we have to work with this regime, that is Alofit. And we analyzed this data that we created both with the good model and with another tool to compute nonlinear scales, which is HM-code. So basically, you have two different tools applied on the same dataset, and the constraints of HM-code that go away from the fiducial cosmology, what is used to generate the data, tell us that using this code on a universe that is modeled another way shows us that there is some mismatch. So we basically go away from what we expect. And this is a problem because Alofit and HM-code are two codes that are, let's say, tuned on lambda CDM and small extensions to it. So they should go kind of well together. And seeing that they actually deviate so much, it's kind of scary for what we want to do with nonlinear scales in the future. The same thing applies for baryon feedback. What I was telling you, there are different models of baryon feedback. That is what these acronyms stand for. And if we use them to analyze a single dataset, we see all different results in different parameters. So this basically tells you that the model you use for your simulation and what you apply it to, it's important to get accurate results. If you have a mismatch, you can get results that are very precise, very tiny error bars, but on a completely wrong value of the parameter. This is an issue that is particularly affecting exploration of extension to lambda CDM. One example that I stumbled upon many times is that of modified gravity. We don't have simulation of n-body simulation for general modified gravity models. We have for some models, we have very few or non-existent for others. So where one wants to constrain modified gravity, the safest thing you can do to avoid inaccuracies, so wrong parameter measurement, is to cut out your nonlinear scales. You take those data, you throw them away. The problem is that you're losing a lot of information. You want to be accurate, but at this point you are not precise anymore. Because, for example, in this paper from the kids' collaboration, you can see that throwing away the nonlinear information there with lensing survey to do modified gravity basically moves you from these dashed contours that you see here to this giant blob that basically tells you anything. Basically, you don't constrain much. So this is an issue, the one on nonlinear scale. Many people are working on it. We're working on emulators. There are some way out on it, but one has to keep it in mind. One has to always be careful of the model that you are trying to investigate if you have theoretical prediction for nonlinear scales for that. Now I want to move on the other side of the scale spectrum and talk about what we called in our recent work, ultra-large scales. So what I was showing you before is how to get your CLs with some approximation, and I've shown you the exact form of how to write these CLs related to the primordial power spectrum. Now I'm at scales where everything is linear. Ultra-large scales means that everything is linear. I can do all my theoretical prediction easily, sort of. So I can write my CLs this way. In this window function, with respect to before, I added in some more terms because indeed we have the density window function that is the one I've shown you before with the bias, the number density of galaxies. so what was there before, but there are some other terms that are based on the velocity, on the peculiar velocities of the object. There are some lensing effect, and these are the general relativistic effects that happen at large scales I was telling you about. So this is actually the correct way of writing the galaxy-galaxy correlation function in this sense. Now, this kind of equation, hidden inside, you have a lot of things. You have transfer functions for the different potential for matter that tell you how this power spectrum evolved. You have different effects like Doppler, magnification given from the lensing effects in between you and the galaxies. And within all here, you have Bessel functions that are used to project in spherical harmonics all these quantities. What is the problem with this? Up to now, I'm saying that I can write everything. The problem is that computing these exact CLs requires like triple integrations that depends on very highly oscillating Bessel functions. So it's something that is technically difficult. So I can write my prediction, but when I do it numerically, it's very slow. This is the issue. And this is an issue because I want to use this prediction to run MCMC, to run chains for different values of cosmological parameters that are like 10,000 iterations, for example. And if I have something very slow, done 10,000 times, it's kind of difficult to go to the end of it. There are some approaches that try to reduce the calculation time using fast Fourier transform, for example. Here are some references. But what one usually does, and it's been done up to now, is that we use approximation. So what approximation do we use? Well, first thing, what I've shown you at the beginning, all these terms, I removed them. You can see that these terms are proportional to 1 over k squared, so are relevant at very large scales. So as long as I'm working with the current surveys, I don't have much interest in this. This will be subdominant. Also, another thing that one does is using the so-called Limber approximation that basically allows you to write the Bessel function kind of in this form when you are high enough multiples, so small enough scales. And putting all this together, I get the CLs that I was showing you before. These are the CLs for galaxy clustering that I've used for my forecast before for Euclid, and those are usually the one that everybody uses. Is this a problem, doing this approximation? Well, relying on this approximation is not a problem as long as the scales where these break down are not tightly constrained. This could be not the issue for future survey. What you see here in black is the exact calculation of the CLs, the one I told you it takes a long time, with all the effects, no approximation, and so on. In green, for the same cosmological parameters, the approximation. When you go at high enough L, so at small scales, these are within the error bars for most of the experiments. When you are at low L, so large scales, this might not be the case. The gray area that you see here is the SKA observatory expected noise on this kind of survey. And you see that we already are at the limit where these actually are relevant, the red and the difference between the red and black. So what we were interested on in this work that I'm citing here is to see if neglecting all these effects has an impact similar to what happens at the nonlinear scale, if it biases my constraint. And we found that this is indeed the case. We did a forecast for the SKA observatory in this case, and we analyzed synthetic data that are created correctly, so with all the effects considered in, and then analyze them with the approximated spectrum. Because we know that we cannot run an MCMC with the exact case. And we found, computing the shift in this way, so a unit of the error that we get on all parameters, that all the parameters are very far away from what we expect. So we have significant shifts on all cosmological parameters, and we need to be careful about this. This is done in a case in which we don't have nuisance, so maybe the significance can go down, but this highlights that future survey will have a problem in having to model these effects. In particular, what we found is that if you go to extension of lambda CDM, so the data set you created is exact and is in lambda CDM model. and then I test for extension with the wrong modeling of the spectra, what I find is detections of non-standard model. For example, I can find non-Gaussianities, I can find W that is different from the cosmological constant, and all this by just having a wrong modeling of the very large scales. So basically, this is the issue that we face. And it's something that comes up with the newest survey with higher sensitivity, larger scales detected, and so on. We cannot make this calculation for a run with MCMC, and if we use the approximation, we get inaccurate results. So what do? Is there a way out of this? So one first option is to cut out the ultra scale like we did with the nonlinear, but we do not want to do that because it's a lot of information there, especially if you want to look at the test of general relativity. We can try to make the calculation faster, and this is something where people are working a lot. I know that there are some progress, but I never tried them, so I'm not an expert on this. We can try to include only the most relevant terms, and we are working on this within Euclid. We should have out something soon for this. But there is an easier way that it's the one we try to test, that is to apply some debiasing technique. There is also a possibility to try different estimators, but what I will focus on is this last one. So the bias and constraint. How do we do this? So basically, the idea that we tried was quite simple. So we know that the CLs exact are expensive. They take a long time. But we can still do them for a limited number of points in our parameter space. We can still work on it. So our idea was to basically write our approximating spectra, not just by themselves, but adding to it at the biasing term. Which is a term that is computed at a single point, θ0, of the parameter space, and is just the difference we expect at that point between the exact and approximated spectrum. So by definition, this means that in θ0, we will have exactly the correct prediction for the spectrum, only at that point. But all the other ones nearby are corrected accordingly. So basically, if we use as our point in which we do this correction, the fiducial, so the expected peak of the distribution, we are allowed to recover the constraint, to move basically the constraint in the right spot. You can say, yes, you can do this on simulation because you know the spot in which you have to plan to put it. But if you go and look at our paper, we have shown that this is feasible also not knowing where this point is, but running a minimization algorithm. So trying to compute the exact spectra only to find the peak of the distribution and then doing the MCMC with the correction. So using this correction basically allows you to move all the constraints where you are supposed to have them. So be accurate again, and also allows you to remove all false detection of your non-standard, your beyond lambda DM models. So the point is that the only thing that we are sure of here is that we are recovering exactly the peak of the distribution. We are not sure to be accurate on the tails of the distribution, because obviously the correction term is exactly valid at the peak and gets less and less valid when you move out to it. So this is something we have to work on. Any questions on this? Or the nonlinear part, whatever you want.
For the nonlinear part, maybe you can say a little bit later. But yeah, what is the difference actually between the halo fit and the HM code? Because you are getting very different results. So I was wondering if you can talk a little bit about this.
So the point is that HM code is an evolution, if you want, on halo fit. It's not using the same approach. It's using the same approach, but it's using a different set of simulation. It also contains some baryon feedback modelization in it, and it should be suited more for non-lambda dark energy models. So for model that moves out of cosmological constants. So that's why, for example, in here, when we did our simulation, we didn't use W to be exactly -1. We moved away from the lambda CDM model exactly to show that when you're not in lambda CDM, this is an issue. If your data are lambda CDM, the distance between the two gets much smaller. So basically, this is a problem that you face when you move out of the standard lambda CDM model.
And they have feedback, baryon feedback, or something like that.
They have a simple modelization of the baryon feedback. It's not that sophisticated as this other model that I've shown here, but there is some modelization of it inside, at least in the latest version. It changed between two versions.
Okay, in the next slide, I guess, where's the key information from that? I was a little bit lost in that. Could you so I'll clarify? What's the main message from this picture here?
So the problem is that if you cut out your nonlinear scales to avoid the problem modeling them, you're removing a lot of information, especially when you deal with modified gravity model, for example. So you're moving from these to the giant blob, and we have nothing.
Okay, I see. And my last question, if I may, it has to do with the ultra large scale modeling. For CMB, we also have, as far as I can say, if I understood correctly, don't we have the same problem for, we can make linear approximation to the very large AL, but we switch to the, at some L, we switch to the full calculation, if I'm not saying anything wrong. So why we can't say, why we cannot do that here? Just compute the linear approximation at very large L, then try to, you know, just switch at some specific point.
No, it's something that you can do, but when you move everything, basically when you consider all the different terms that I've considered here, sorry, basically in these parts here, in this term that I'm neglecting, if you do without the linear approximation, only the density one, I think it's feasible. When you start adding these other terms, which are other integrals on top of these, it becomes a little bit tricky and slow. I mean, you can do that, it's just low.
Yes.
We managed to run a minimization with that. Yeah.
In fact, I'm trying to do that with the lens.
Yeah, okay.
In terms of feasibility, it's easy. You can actually do that. Just that it's very slow.
And in this not happened with CMB because that there isn't this term in CMB, right?
So like some of these terms, for example, like some of these terms depend, for example, of the width of the redshift beam in which you are integrating this part. So like with CMB, you don't have this issue because the redshift you want is all projected at the redshift of the last scattering. Instead, here you're taking things that are quite wide, and some of these effects can become relevant, especially in the lensing part and so on. Basically, if you remove one effect, like narrowing down your beam, then the other one pops out. It's a bad interplay between things here.
Okay, I see. Okay, thanks.
Yeah.
Hey, we also have a question. Please go ahead.
Hi, Matteo. It's Nicole. I would like to ask you if in this data, if is encoded also the Cepheid information. I mean, when you use your data, I think you have to determine the distance of the object, right? So in this information, you use the shows detection of each knot or what?
No. In this case, no. All our cosmological parameters are assumed. Like, I'm assuming a fiducial cosmology when we create our data, and we assume obviously the Planck values. But the point is that here I'm not really like this would be an issue if I was relying on BAO data from the spectroscopic surveys of Euclid, for example. Here it's different. I'm not using information that is coming from background survey. I'm only using the galaxy clustering and weak lensing correlation. And these you can see, for example, here.
So it's like angular correlation. So you don't need the distance information, right?
Exactly. This you can see it here because, for example, if you look at weak lensing alone, which is the blue, you see that H is totally unconstrained. I mean, it's very poorly constrained. So it means that there is no information from outside. All the information that we get on age basically comes from. So that's
right. So Euclid can play a nice role in the each node determination.
Yeah, indeed.
It's independent. Okay, thank you.
You're welcome. Okay, if there are no other questions, I want to briefly show you something for the more distant future and then summarize a little bit. So this is something that I worked on recently. The paper came out a couple of weeks ago, and basically wants to look at another thing that is very, very trendy in recent years, which is gravitational waves astronomy. So basically, you know that since its first observation, everybody started to work in gravitational waves, myself included, and everybody's interested now in this because it's a completely new observation, comes from a different set of observation, different nuisance, different systematics. It's very helpful for something like this. And in general, people want to look at gravitational waves because observing them, observing a binary events merging, gives us an estimate of the luminosity distance. So it's a measure of a distance, and it's already been thought that this could be another thing, like Mikol was saying, that can tell us about the tension in each node. But there is another thing that happens with gravitational waves. Since, like, in general, the redshift can be higher than the one of supernova, we expect a little bit more effect of lensing on this kind of observation. So gravitational lensing impacting the luminosity distance. This is usually seen as a nuisance because it doesn't show you the real value of the luminosity distance. But if you're able to get a mean value at the L bar, that is the mean value of the luminosity distance, you can try to measure the distribution of this lensing effect on the sky. Basically, this delta L that will tell you the convergence field on the sky, which is related to the shear field, and you can try to probe the large-scale structure, also just observing gravitational waves. So what we have shown here in this work was how to try and get a 6 time to point correlation function. So in which we have galaxy clustering, weak lensing, the cross correlation, but also the gravitational wave lensing, the kappa field coming from gravitational wave. And this can be encoded in the same formalism and try to be exploited to add extra information on the large-scale structure. So in our exploration, what we did was to try to add the two together, gravitational wave and galaxies, and try to see when do gravitational waves get important. So we try to vary the number and the error that you have on the luminosity distance, and try to add them for different sets, observational sets to galaxies. And basically what you see is that for a given number of specification, the constraints on parameters, 0 is sigma 8, doesn't vary. So this means that all the information is coming from gravitational wave. Then at a certain point, when you have enough statistics with a low enough error, you start to improve on galaxy surveys just by using the lensing of gravitational waves. This is just lensing. There is no information on the background coming from it. So basically, you see, this is very futuristic because like 10 to the 5 gravitational wave, maybe Einstein telescope, not even given that it will give us something like that. But it's something that we can look forward in the future, because if you look at how the constraint behave on cosmological parameters, you see that adding this new observable to galaxy survey actually helps in tightening up the constraint. And it's important to do this because it's a completely different set of systematics. So having a comparison between the two is definitely helpful. So it's something that in the more distant future can become important for cosmology. Okay, so let me finish up by summarizing a little bit. These are a few, I noticed that I had quite a few take-home messages written in this slide, and I also noticed that they are very divided in, as I was saying, I divided my talk, optimistic and pessimistic. So in the first part, what I tried to tell you is that the large-scale structural surveys that we will have, photometric, spectroscopic survey, will put us more in the precision cosmology era. We will have a fantastic statistic coming from the photometric survey, And the cross correlation between different probes will be extremely helpful to cosmology. Will give us the opportunity to break the generalities with nuisance parameter, measure something about astrophysics, and obviously cosmology. The problem, the main message that I try to give with this presentation is that we have to face new problems. There are problems, even though maybe not totally new, like the nonlinear scales problem, are becoming more and more pressing if we want to fully exploit the potential of the service that we will have. And I've shown you that bad modeling, both at the small scales and at large scales, can give you still precision cosmology, but not accuracy cosmology, which we have to care for also. And we can try, I mean, I show you one simple debiasing method, but the road ahead to this kind of problem is still long, and we have to fix it. And finally, I just wanted to show you what in the deep future we'll be able to do also with gravitational wave, but also here, who knows what other problems we will have to face and what we need to do. And we stop here. Thank you.
Okay, many thanks, Matteo. So I will open for questions. If you guys have questions, some of them have been already asked during the seminar, but if you have more questions. Okay, I can start, and if you want to ask more questions, please raise your hand virtually. And regarding these ultra large scales, you say that what we did now is not taking into account the other transfer functions from velocity, lensing, and so on.
Well, actually, the point is that when we create the data, we account for those effects in creating the data. So when we have this black line, this black line, this takes everything into account. So it has the extra effect, relativistic effect, and so on. It's when we do the analysis we remove it. So all these effects are accounted for when we compute the biasing factor. Here, all the
okay,
difference.
Yeah, my question is there a kind of hierarchy which would be the second, the most important, if we go to, I mean, in the sense that I can run the approximation, take into account one more, just to have not so many problems with computational time.
So in principle, yes, but it all depends on your survey. So this is the structure that we use for our SKA-like survey. This is the number density of galaxy and how we binned it. The effect that dominates, so the one that you have to be careful to take into account, changes depending, for example, on your binning strategy. As I was saying before, if your bin gets wider, you have more lensing effect, and maybe less space distortion, or vice versa. So how you bin, what's your photometric redshift error, all these kind of things enter in in which one is the most important effect. So it's not something that you can know a priori. We are trying, for example, now within Euclid, and it's something that we should have out soonish, let's say, to account for, this redshift space distortion one. So to add in the approximated version, at least the redshift space distortion. There is a way to work it out, and it's done in the works of Stefano Camera and Konstantinos Stanidis that work on this, and there is a way to take it into account. So at least this one we are trying. Let's see what effect.
Okay, and if I may ask one more question, I mean, just to take advantage of your experience in this practical part, I would like to comment from the practical part. I mean, building likelihoods and codes. Could you state the difficulties that photometric surveys add in the data? I mean, where should we take into account the error on the redshifts and I mean, just a basic comment.
Oh, sure. No, I mean, the point of the photometric surveys themselves, when you build basically your CLs, where your error enter in, it's something that is encoded here. It's something that when you build your CL here, you have this end that is the galaxy distributed, binned galaxy distribution, so that you can build your CL binned in Redshift. And all the information that you have on the error, that you have on the Redshift, on the outliers, all nuisance parameters that are related to this measurement enter in this one. So now, for example, also in Euclid, and also it's something that we are working on for the release of Cosmic Fish that I was telling you before, is trying to put here some nuisance parameter that deal a little bit with the mistakes that you can do in Redshift determination given the photometric observation. So this is a characteristic feature of photometric survey, if you want, that you have to include all your errors here. Another distinctive characteristic is that you can work with this kind of probe, the cosmic shear, which worsens your problem of nonlinear scales, of having to deal with the nonlinear scales. This is because with the photometric observation, we can go to very small scales. So we have data coming from there, and we need to model them to not throw it out. With the spectroscopic survey, this is a little less pressing as a problem, because like there are works in which they try to model the nonlinear scale at which spectroscopic surveys are interested in a perturbation theory kind of way, but this is not something that you can do on the photometric one because you go deeper in the nonlinear scales. So it's one issue that here is much more important, let's say.
I see. Many thanks. So do we have more questions?
Yeah, just a clarification question, a very quick one. You said the Euclid survey is both photometric and also spectroscopy? Okay.
Yeah, we'll have two different surveys. It's basically two different instruments that are mounted on the satellite. So then we will have both a spectroscopic and a photometric survey. Obviously, you expect different statistics between the two because of the different way the observations are done. But the idea behind the Euclid satellite is really to try to include all this information together. So for example, one thing that is still on the works, but there is hope that we will do something about it, is to try also to consider the cross-correlation between the spectroscopic and the photometric survey. This is something that is technically difficult, if you want, because they are not done in the same way. One is a 3D information, one is a projected 2D, but we are trying to work in a way to cross-correlate these two, because in the end, you're looking at galaxies in the same field of view, so you know that there should be a cross-correlation there, and we want to see if it adds any information or not.
So this wouldn't be double counting, something like that?
In principle, it depends on how you deal with that. And so the point is that, for example, when we did these constraints for the Euclid survey, when we combined galaxy clustering spectroscopic and the photometric one, we removed the redshift range in which the two were overlapping. So exactly not to do double counting. So this means removing information from one or the other. But if you consider the cross correlation between the two, this should not be double counting. Any actually double information should be accounted for in the cross correlation.
So the key thing is do the correlation correctly, like model this correctly. Okay.
Because if you just add them up naively, it's possible that you are double counting information.
Okay, I see. Thanks, Professor, for the very nice talk. I learned quite a lot. Thank you.
Okay, let me see if we have more questions. It seems that we don't. So let me thank you, Matteo, for a very nice seminar, and it was very clarifying. Thank you.
Thank you for inviting me.